So guys, today I will talk about this isoperimetric problem that we wanted to discuss the other day. Okay, so here we have this kind of problem. Given uh, a rope, let's say a rope of fixed length, say L, a rope of fixed length L. I want to make a closed path out of it. So let's consider A and B. And what is the area enclosed by this? So I want the isoperimetric problem asks for the shape of this rope of length L such that it encloses maximum area. So let's write down what it means. Let L be the perimeter. So by the formula for arc length, we know that is integral from, let's say this has got x coordinate x1 to x2 ds, but still I haven't introduced the x variable as the integrand, so let's write it as integral root of 1 plus y dash square dx. Now this is in standard form, which we know the arc length formula is 1 plus y dash whole square dx. So that means implicitly we are understanding that y is equal to f of x is the plane curve which is giving this shape, right? So eventually I want to know what is this function. So basically we are studying this by the calculus of variation format. So there is a problem under the calculus of variations again. So what we do, let's write this equation as 1, and we also know that the area functional is given by integral y dx, right? Y dx, again from x1 to x2. So we want to consider these two equations. So that means, what do I want to do? I want to maximize the area, this area, subject to the constraint 1. What is the constraint 1? Is that this length is fixed. So whenever this kind of coupling comes, we need to use the Lagrange multiplier. So what is to be done here is that we consider a new functional f, which involves this kind of a functionals f plus lambda g, where f is the functional corresponding to this one, and g is the functional corresponding to the earlier one, the arc length element, right? So this is your uh, functional to be used for the Euler equations. We all know last time I discussed that we need to understand the Euler-Lagrange theory, Euler-Lagrange equations in the calculus of variation setup. So what we do this by using the Lagrange multiplier, where I'm using f for the functional y, g for the functional corresponding to the arc length element, and lambda is a Lagrange multiplier, so it's a constant. So here, note, Lagrange is a constant. Lagrange multiplier is a constant. Okay, so uh, correspondingly, the Euler-Lagrange theory says that we get this as the corresponding Euler-Lagrange equation, d by dy of dou f by dou y dash equal to 0. So just look up into the theory that I spoke in the class. So that gives you this equation. So this implies, so if you substitute place of f my functional f plus lambda g, that is, let me not directly write the implication here, my f can be understood as y plus lambda times root of 1 plus y dash the whole square, correct? So therefore, this let's say this is 3. 3 implies, see, because I'm taking dou f by dou y, this is just 1 plus lambda times, I need to, okay, let me not confuse you much. I'll just keep this lambda inside because I want to just mimic this. I think I made a mistake. It's d by dx. D by dx of dou f by dou y dash. So I have to take the partial of this whole functional with respect to y dash. So that becomes lambda y dash divided by root 1 plus y dash whole square is equal to 0. So yeah, one can check what exactly did I do. Lambda is a constant. Root of 1 plus y dash the whole square, derivative is 2y dash divided by 2 root 1 plus y dash whole square, and that 2 gets cancelled, and therefore what I get for this particular brace is this. Okay, so now my next task is to do the ordinary derivative, d by dx of this. There I'm going to use the product quotient rule, quotient rule. So what I'll do, by the way, again I think I made a sign mistake. It has to be minus. So it's not plus. 1 minus. Now this d by dx is what I'm going to write it out here. So I'll take lambda totally outside. So I have this denominator, root 1 plus y dash whole square times the the derivative of the numerator while lambda is out is what? Y double dash minus, now the numerator has to be uh, written and the denominator has to be differentiated, which is 1 divided by 2 root 1 plus y dash whole square into 2y dash. Remember it is d by dx, so you should also write y double dash. So this 2 is cancelled, and so I'm sorry, I don't have space to complete the bracket here. So this is what? This whole thing is 0. This whole thing is 0. This implies 1 minus lambda times uh yeah, I'll just simplify this. Lambda times, what I am simplifying here is this. I'll take the the LCM. So that becomes root and root leads to 1 plus y dash whole square times y double dash minus, here you see y dash the whole square times y double dash the whole divided by the whole divided by oh my god, I think I yeah, so this quotient rule I haven't, this is just the numerator of the differentiation. Look, you have something, the the quotient rule is g f dash minus f g dash divided by g square, that kind of a thing. So you have this 1 plus y dash the whole square also here. So sorry, I forgot that. So this turns out to be 1 plus y dash the whole square, the whole power 3 by 2. So we are almost close to understanding what happens here. This implies 1 minus lambda. So you can see that this y dash square y double dash and y dash square y double dash gets cancelled. So what remains is 1 minus lambda y double dash the whole divided by sorry, it's not whole divided by 1 minus lambda y double dash divided by root of 1 plus y dash the whole square. It's it's not root. Root is gone long ago. It's 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 1 plus y dash the whole square, the whole power 3 by 2 is equal to 0. So I can say 1 equal to lambda y double dash by 1 plus y dash the whole square, the whole power 3 by 2. This implies that 1 by lambda is y double dash by 1 plus y dash the whole square, the whole power 3 by 2. So you see something very familiar here, that if you reciprocate this, you see that it is 1 plus the derivative square, the whole power 3 by 2 divided by the second derivative. Doesn't it sound very familiar? So this sound, yeah, this right hand side is actually here. RHS is actually giving rise to simply the radius of curvature, or whatever that y is. So if y is such a function whose radius of curvature is absolutely lambda everywhere, so what should that curve be? So hence y is such a function whose whose radius of curvature is constant. And what is that such a function? What is that curve? Such a function, I would say curve. Definitely such a y is Indeed, a circle. Indeed, it's a circle. So that's it. So this is what is called the Dido's problem, fixed rope. So I'm idealizing it to be a one-dimensional curve, and that curve has to be has has to close up like a circle. Only then it will enclose max area. That's what the problem is about. So this is isoperimetric problem for you. Now let me just talk in the next 2 3 minutes that there's some more such problems under the guise of isoperimetric problems. For instance, uh, let's say I have uh, a fixed volume of gas which is inflating a balloon, or let's say it's uh, a soap bubble. A soap bubble formation, I could say. So there's some gas being trapped in some bubble or something like that, in some uh, compact uh, compact convex body. So what is the shape of such a convex body such that its surface area is minimized? Okay, so soap bubbles are such examples where volume V is fixed. Volume V is fixed. Find a compact convex body whose volume is fixed and surface area is minimized. So this is also similar to the isoperimetric problem where we are generalizing whatever we had spoken about length in the earlier problem. Now we are talking about volume being constant, and we are varying the shapes and seeing for which shape do we get minimum surface area as opposed to maximum area earlier. So this leads to the this the soap bubble kind of structures, which are in mathematical literature called minimal surfaces. So there is a nice theory people can get into this thing. Basically, what happens is that this this can be likened to a membrane kind of a thing. This membrane is holding, let's say, the gas particles inside. So this, supposing that, of course, it's a uniform, same kind of a gas being trapped inside. So there's a uniform distribution of the pressure, and due to that, you can see that the membrane, once it attains an equilibrium, it has some it has some constraint, and the constraint being that the volume is fixed, uh, yet it has to minimize the energy, uh, and therefore what happens is you get a certain shape called the soap bubble, and these are examples of minimal surfaces. So thank you, guys. So there's another example I wanted to say. Another example for another example for isoperimetric problem.